Starters. What are two types of loops in Python? For loops and while loops. All right. What's the difference between a list and a dictionary in Python?
Dictionary gives you a key and value.
All right. So dictionaries are collections of key value pairs. Lists are what? Or who? Okay, so we're just going to say collections of values. So dictionaries allow us to hold a bunch of pairs. So we could have first name is Mike, last name is Littman, that kind of stuff, where lists hold collections of things. So you could have like a 1, 2, 3 in a list. Where in a dictionary, we might have Mike, or F name is Mike, L name is Littman, something like that, and these guys are in curly braces. That makes sense? So key value pairs, this is a key, this is a value, where lists just hold a bunch of values. All right, and this guy, convert from binary to hex. DF? A, B, C, D, right? This is the ones place, the fours place, the eights place. This is 12, 13. 10, 11, 12, 13, fourth letter A, B, C, D. So this is D, F. Remember the shortcut we learned last time? You can break this into groups of 4. 1, 0, 1, 1, 0, 1, 1, 0, 1 is the number 13, which is a D. 1, 1, 1, 1 is a 15, which is an F. So the answer is DF, like that. The other thing you can do if you wanted to do it the long-winded way is you would have converted this guy first to decimal, right? So this guy to decimal, let me just give myself a second page here to do that. All right, so this is a 1 in the ones place, plus a 1 in the twos place, plus a 1 in the fours place, plus a 1 in the eights place, plus a 1 in the 16s, I'm sorry, I'm screwed up here. 1 in the twos place, plus, I'm saying it, typing exactly what I'm saying. So 1 in the ones place, plus a 1 in the twos place, plus a 1 in the fours place, plus a 1 in the eights place, plus a 1 in the 16s place, plus a 0 in the 32s, plus a 1 in the 64s, plus a 1 in the 128s. So you would add all that together. So that gets you 223. So that's the decimal value, 223. All right, then to convert the decimal value, 223, into hex, we would take 223, we divide it by 16. So 220, is that what I get, 223? 223. 223 divided by 16 goes in 13 times. 13 times 16 gives me 208. So that's remainder 15. 13 divided by 16, 16 goes into 13 0 times. 0 times 16 is 0, remainder 13. So this is a D, this is an F. Then we read it from bottom up, DF. Make sense? All right, so either one of those ways would have worked. Obviously, this one's friendlier, right? So I specifically gave you hex or binary to hex so that you would be able to use the trick. If you didn't use the trick, that's fine. I'm not going to grade you down if you got the right answer, but
You shouldn't use the trick. So
didn't I teach you the trick last class?
I use the long way 6 times.
Well, didn't I teach you the trick last class? So why do you think you couldn't use the trick?
I can because last time you said yeah. Yeah.
When we were doing the example in class.
Yeah, you said
Because I said in class that if you know the trick, don't use it this time. I'll show you the trick in a minute. Well, that's fine. Well, that's fine. This didn't take very long to do it the long way either. So, because the first two shouldn't have taken very long, right? If you did the readings, these two should have been pretty easy. Now, I did find it interesting when I went through the book. Not everybody bought the book, which is interesting. And then on top of that, you were supposed to read chapters 1 through 5, right? And do all the interactive stuff. So chapter 1, 95% of the people did everything. Chapter 2, 96% did everything. Chapter 3, 75%. Chapter 4, 73%. Chapter 5, 63%. So if you had a week to do 5 chapters, why was there a drop-off in participation in the last chapters? Because I'm going to be able to see who actually bought the book and who did the stuff. And then it's going to be pretty interesting when I see screenshots if you turned in the same screenshot as your classmates because you just used their book. Yeah, so that could be fun. I did tell you last time I was going to be able to track it too, didn't I? Remember that? Yeah, what's up?
You sent a screenshot, but we don't specifically know the type of screenshots we have to submit. Because some people will like, if they finish each activity, they will take a screenshot. So some people, we are submitting the one that shows percentage.
Okay.
So I don't know the one we're supposed to submit.
You don't know the one that you're supposed to submit. Submit screenshots at the end of each chapter. So let's see. This would be the end of the chapter. That's the last thing of the chapter. So after you fill out this one, because that's the end of the chapter. And then that for all the other chapters. So this one as well. This one as well. So I don't know.
I did it, then I changed it. I take screenshots for the stage of war.
Okay, that's fine.
Yeah.
That's fine.
I will ask about Mendix. I completed this week.
Mm-hmm.
And now, when I send the link for somebody to open it, it asks him about the password and
Oh, probably maybe it wants them to create a Mendix account to view it. My guess is it wanted them to create a Mendix account in order to view it.
oh, I sent it to you. I completed all. I sent it to you. Then after a while, I tried to enter to it to see my work. It asked me to get the Mendix local account. Mendix local account. So if you couldn't get to see, that would be, I think.
Well, I haven't looked at it yet, but I mean, I can go into each person's account.
You can?
Yeah, I have access to your direct account, so it'll be fine. Okay, so quiz should have been pretty easy. Should have been free points. All right, so let's keep trucking from before. Let's see where we left off here. So we did a lot of number conversion stuff last time. We've been talking about history of programming languages, so let's get through the rest of that so that we can get into the Python stuff today. Because, man, I have a nasty assignment for you for next week. Oh, yeah. Huh? Why wouldn't we meet next week? Oh, well, yeah, but it's only going to be an hour. It's a 4-hour class. Right?
You said last year assignment. That means it's going to take time. So we might not be able to revise what we've been doing from week 1 to week 3. So if it's that nasty.
Well, actually, I don't think the midterm is going to be the next week. I think the midterm is going to be the first hour of week 5 because it's going to cover everything from week 1 through 4. So it won't be next week. It'll be the first hour of the week after next. But you'll still have a homework assignment next week for the week after. Hey, this is a compressed class. We can't, it's just the way it is. Suck it up. All right, so we talked about all these web languages, right? So we have all of these server-side languages, Perl, PHP, Ruby, Python, Node.js. We kind of talked about the strengths and weaknesses of these guys. Not that one language is necessarily better or worse than another, but, you know, Perl was a language that existed before the internet, so it wasn't necessarily created with the internet in mind. So PHP said, hey, look, we have a lot of people writing stuff specifically for the web now, so let's build some tools in that allow them to do web stuff. Okay, Ruby fixed some problems from PHP. That is that PHP didn't allow you to separate. We talked about MVC, Model View Controller. It didn't allow you to separate your logic from your interface. Now you can do that with PHP. There's some third-party stuff. So Ruby said, okay, I'm going to fix that problem. We're going to have an embedded template engine. And then on top of that, Ruby also came with its own web server. So you didn't have to solve the IT problem of getting your development environment up and running. And we're going to look at a development environment today for Python. So in any case, Ruby made it easy to just jump in and start developing. Okay. Well, Ruby was very, 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 very web specific. Okay, so it's a great tool for creating web applications, but as we kind of got more mature in the things that we were using the internet for, more than just the website, we started creating third-party APIs, things like this. We needed a language that was a little bit more well-rounded. So Python kind of maybe even takes a step back. It does less stuff for you, and we're going to be using Python in here. Because it really is a general purpose programming language. But at the same time, it has a tool built into it called pip that allows us to kind of conveniently add third-party things to our web application if we're going to be using that, or third-party things to our non-web application if we're writing something that's either command line or a server or something like that. Then Node.js is kind of the newest, coolest kid. And what we talked about related to that was you have this issue here where we have server-side versus client-side programmers. So client-side programmers are the folks that try to make the websites look pretty, right? And then you also have some functionality on a web page, maybe for web forms. We have to make sure that they, we have to validate the web forms, make sure they put in their username and password before we actually send blank information over to the server to check. Well, so the folks who are web side or client side folks, they know HTML pretty well, and then the language that they work with, the actual programming language, would be JavaScript. That's the one they're comfortable with. So pretty often you would have client side and server side folk having to kind of communicate with each other. And then what would end up happening is you would have these people sometimes kind of moving over here to the server side and saying, hey, I want to dabble in some of the server-side stuff and make the back end for my front-end web page. Well, Node.js said, hey, we have some problems we need to fix from Python anyways, or from some of these other languages, because we're running a lot more servers. We need multiple things connected at once. This is an event-driven thing, whatever that means. Don't even worry about that. But, so we're going to upgrade the language anyways, but at the same time, we're going to have the programming language for this technology be the same programming language that the client-side developers are already used to. They can kind of jump in and get into that language more quickly because they aren't having to take something that they've done all their working career, and then all of a sudden they're having to learn a brand new language, because a lot of times the folks that are over here on the web side of things are kind of hybrids. They're not necessarily full-blown programmers. They're kind of designers who are also programmers. So they might not have the strongest programming background, and therefore learning another language might not come as easily as it might come for somebody who's a programmer. Okay, so that's all of our web stuff. Well, then we started talking about our native languages. So we talked about C. C is a procedural language. We mentioned kind of like we use the example of a telephone, right? Pile of wires. We see all the details. So C, being a procedural language, has variables, so name value pairs. It also has arrays, which is a collection of type variables. So this is kind of like Python's lists, now that you've read about lists. So an array is like a list. Structs are like dictionaries. Make sense? So now we're connecting some of those dots. But keep in mind that these are really old. Right? This is from late 60s, like 1968 or something like that is when the C language came out. And I like to teach the history of programming from the perspective of C. Wasn't the very first programming language, but from modern day programming's perspective, it's the first language that mattered.
Why do you think it's still so popular?
I'm not.
Because many systems are still based on it.
Well, I guess define popular. I'm not sure it's that popular today.
I always see like a lot of, for example, like even searching for jobs, I always get out there, like, oh yeah, they want somebody who's very strong in C.
Yeah, so a lot of systems programming. So if you're writing, especially in the IT industry, if you're writing stuff directly to communicate directly with the operating system, a lot of server-based operating systems are running Unix. C would be the go-to language because all of the libraries are written in C. So like in the undergrad right now, I'm teaching our 450 class, which is systems programming, and we're using C in there. So it's not so much that it's popular, it's kind of just the right tool for the job because Unix is a really good operating system. It's been around for a really long time, and since it's been around for so long, most of its crap is written in C. Right. Where if it was, 3 years old, it would be written in C# or something like that. So if you're a systems programmer, let's say for Windows, especially today, you would probably interface with the operating system through the .NET architecture, so you would probably write system stuff using C#, a much more modern language. The other thing, reason C would be popular as well as C++, probably really the two of those, but would be in-game programming. That's where things need to be really fast. So you start moving away from this cross-platform stuff that we'll talk about today. We talked about C# versus Java. I just kind of gave myself some starter slides to get into that. So really think of this as an old language. And the reason I like to teach this is kind of the starting point is, and this is kind of like you pointed out, maybe popular is the wrong word, but C is very much a usable language today. It's a powerful programming language, and don't mistake it that these languages are based on C. You see C written all over them. All these more modern languages have done is kind of protect the programmer from not the pitfalls of C, but the difficulties of C. I think you could make the argument that C++ made a lot of sense because, when you were, C came out in the late 60s when, we didn't have a lot of memory, we didn't have a lot of computing power. And because of that, the programs, and also computing was relatively young. So the programs that we were imagining and the programs we could actually write, given the hardware we had, were fairly primitive compared to what we write today. The video games you see today, or the latest, greatest version of Windows, or the latest, greatest version of Microsoft Word, are way more complex today than they were in 1970. Make sense? Okay. We have a lot more powerful hardware. We have a lot more memory. We have a lot more everything. And the languages have kind of had to evolve with that. So back in 1968, if we want to just think about this in, in terms of, C is kind of like using a rock to hammer stuff in. All right. Where a more modern language like Java or C#, you'd actually have a hammer that's like made to, then you probably have the little thing to protect your thumb so you don't hit it. They just have added stuff to make our lives easier. But C very much is still an important language, but we're going to see that we never really left the C language. Almost all of it's still there. We've just put some, child safety stuff on there. But C++ makes a lot of sense. We were talking about our procedural version of the telephone. So as we started solving more complex problems, we started seeing that C started getting scary pretty quick. Our programs were kind of hard to manage because you were having to write it all in this one giant file, relatively speaking. You could have had it split across multiple files, but just to exaggerate the example, you had this really scary, program written in here. All the details are just sitting there right in front of you, and unless you had been working on it day in, day out for several weeks, and it was very familiar to you, coming back to this 6 months later would have been tough. You would have probably spent 6 or 7 hours just getting back up to speed with this pile of crap. Make sense? It just wasn't built for making things that complex and being understandable by people. So when we move over to C++, kind of it's not the first object-oriented language, but let's say it's the first object-oriented programming language based on C, which I've kind of started off with this idea that C is really important. Okay? So it gave us an object-oriented version of C. And what does it mean for a language to be object-oriented? If that had made the quiz today, what makes C object-oriented versus C?
Follows OOPS principles.
Say this again?
Follows OOPS principles, like abstraction, inheritance,
Okay.
polymorphism.
Okay. So you're talking really a lot of the tools that it provides. I think really the abstraction piece is the important one. So I like to teach about, typically if somebody's looking at a procedural programming language versus an object-oriented programming language, and this is I think fairly true for a lot of technology. We have these fancy words or fancy phrases that we apply to technology, and a lot of times it's just for show. We're actually using these fancy things to talk about very, very simple concepts. The difference between C and C++ is a container. In C++, they gave us this new container called the class that we can stuff all those wires into, shut the lid, and then poke little holes in it so the public components that we actually need to interface with, like the handset for the telephone and the buttons, those things, are usable. But when we pick it up, there's the telephone. All those scary wires are inside there. At the simplest level, that's what an object-oriented language is. They gave you a new bucket to put stuff in. It's an organizational model. Humans use it all the time, right? You can throw all your crap on the floor in your room, then your room gets really messy, so what do? You kick it under the bed so nobody knows. You get some storage containers or something like that to organize things. That's what object-oriented language brought to the table. And then as part of that, they gave you some tools like inheritance and interfaces and some other things that made working with those objects, those new containers, convenient. Okay. Now, we mentioned last time, so if we kind of just look at C++ here, so still had the variables, still had the arrays, still had the structs. They introduced, this is that new container, okay, called a class. Okay, that's the new bucket they gave us. And the problem with C++, if we were going to say what's weak about it, is it empowered the programmer to make bad decisions. All right, so with languages like C and C++, so if we kind of just look at these two languages, and this kind of goes back to what you were saying about why are these, these somewhat popular today, is these two languages, I would say, are more powerful than some of these newer languages. And what I mean by powerful is they give you direct access to memory. In C and C++, you can directly change buckets of system RAM. So that is great if you know what you're doing. It's dangerous if you don't, right? Because you might be overwriting a part of the operating system or something like that. Have you ever heard of a buffer overflow? So buffer overflow, a lot of times it's associated with an attack. Hackers, things like that, says, I'm going to go to a place in memory, and maybe I know this place in memory has 10 things there. I'm going to go to bucket 11. I'm going to start injecting code there, knowing that at some point, maybe the operating system is going to read from that place and bring something that I put there in when it wasn't expecting me to be the one who left something there. So languages like C and C++ give you direct access to memory. So if you know the right place to go in an operating system, which can be a little dangerous with some of these open source operating systems like a Linux or something, because you can go and look at the source code for it and see how it works. So the people who write Linux, who write that operating system, they need to be pretty careful because they know that they have a public audience that can view their code, and They need to write stuff in a dynamic way and not say, oh, well, I'm just going to hard code it because it's convenient. Because all of a sudden you can say, well, if you're just going to hard code some value right here because it's convenient, well, all of a sudden people are going to come and start, they can manipulate this. A lot of video games that get hacked, that's how they work. Because one of the tricks that video game companies use to make things very fast is they don't rely on dynamic memory. They don't, because if a video game is saying, okay, I need to create a new place to hold some information. Well, if they have to ask the operating system to give me a memory address capable of holding 32 bits, something like that, you're going to get then a dynamic memory address, but that takes time. Because you're having to phone up the operating system and say, Windows, I need 32 bits of memory. So however much time that takes, it's going to be, some number of, microseconds, but that adds up, right? If you do that enough times. Now, on top of that, there's also a performance benefit if stuff in memory is right next to each other. When you're playing a video game or something and it's doing a lot of reads and writes. All right, so you'd want to have all your crap right next to each other. So from a performance perspective, for a video game, it would make sense for the game writers to go ahead and say, oh, okay, well, then I'm going to just say my game lives in this chunk of memory. I'm going to take these first 30 buckets, and that's where I'm going to store some special information. Okay, this memory address, this memory address, this memory address. So only the internal programmer knows where those addresses were, and they can write right to them. Now, if you are somebody who wants to cheat at one of these video games, if you can determine what information is stored at those couple of memory locations, you can go in and modify that information, inject new information into those places so that the next time the video game goes and tries to read some piece of information from this bucket, it might not be the video game that put that piece of information there. It might be your cheating software or something like that. Right? So performance versus maybe security, some kind of interesting stuff. But in any case, C and C++, very powerful languages because they give you direct access to memory. They're also very dangerous languages because they give you direct access to memory. Okay? On top of that, C and C++, well, really C++ is where I make the argument, but both of them do this. I said empowers the programmer to make bad decisions. And the example I typically use is, let's say you're having a party or something, and you're inviting me to your house. In real life, you would always hand me a piece of paper that says, here's my address. Party starts at 8. In a language like C or C++, you can choose to hand me the house. That would never make sense in real life. Houses are heavy. We would never hand somebody a house. Okay? Now, a good programmer in C or C++ would know better and say, I'm going to give him the house, so I'm going to hand him the address of that house. He can go and find it in memory because we have direct access to memory, no problem, because that's the right way to do it. But if you're a beginning programmer and you're using C or C++, the right way to do something and the way you do it might not be the same thing. Because you're going to see when we start doing the Python stuff, you're going to make a lot of mistakes. It's going to be very difficult for you because you're beginners. All right? So with that in mind, a beginner programmer might think they're doing the right thing by passing the actual house. And a language like C and C++ won't stop them. Now, with today's amount of memory, maybe that's not the end of the world. So we got room. We got room for the house, so we can do it. But we roll back. I mentioned last time about the cost of memory, what it used to be. Talk about 1996 RAM was like $1,000 for 8 megabytes. I mentioned that last time. Yeah. So memory used to, and it was even more expensive before that. It used to be crazy expensive. Well, now memory's dirt cheap. We got tons of it, right? The only thing that's limiting us on memory is how many sticks of memory the computer that we have will take. The cost of memory itself isn't really prohibitive. Get 8 gigs of RAM for $40 or something like that. And now you just need to have a machine that can accept the extra RAM. Okay. So given that the job of any of these programming languages, if we go all the way back here, and we talk about how humans solve problems. We talked about the mapping. And we think about what a programming language is trying to do. It's trying to allow us to solve problems the way we already solve them. So a programming language is a power tool for us to use so that we can more conveniently communicate to a computer, tell a computer what to do. With that in mind, if in real life we would always hand somebody the address to a house, wouldn't it make sense that the language should encourage us to do that? Sure. Now, having said that, every now and then, because computers are magical, right? Every now and then, we might have a good reason to deviate slightly from the way we might solve a problem in real life. Because with computers, we could. Right? We could do that. We used an example a few minutes ago for the video game people. They're going out of their way to make the thing really, really fast. And because of that, they're doing it in a way that's not really the most convenient way of doing it. But they're making that choice. They're saying, okay, I need speed, therefore I'm not going to use the stock tools. I'm going to kind of do my own thing. All right, so if the job of a programming language is to be a power tool to the end user, we rely on them to make life as easy as possible for us. Because learning programming is hard already. We don't need it to be any more difficult. Right? And we actually have life's even better nowadays when we deal with the size of, or we deal with older languages like C, because our operating systems protect us. They protect the operating system itself. It sits in protected memory that even a language like C can't write to. So years and years and years ago, if you would have learned C in the late 70s or 80s or even early 90s, if you wrote a bug into your code, your machine might crash. And then you have to restart your computer in order to program some more. Because you might have just overwritten part of your operating system in memory. So you have to restart your computer to have it reload your operating system into RAM.
How long ago?
90s? Yeah, I mean, so this was a legitimate issue, right? That you could crash your computer with that program. Blue screen of deaths all over the place. So, we talk about with Windows that you get blue screens of death too often, right? Okay, those are the professional programmers, the best programmers in the world that are introducing that sometimes. What do you think the beginning programmer is going to do? Computers reboot pretty often. It's pretty funny, actually. Especially when you had the kid who forgot to save. All right, so that's where we look at a language like Java. So Java, still an object-oriented language, just like C++. Still has variables, just like C and C++. Still has arrays, just like C and C++. Still has a class, just like C++. Notice, though, it has gotten rid of this idea of a struct. Now, the Java folk would make the argument, oh, well, you don't need a struct because a class is kind of an upgrade to a struct. So we would say that, I think I have an example here. So with a struct, you can have a bunch of information, name value pairs or key value pairs, as your book refers to it, with dictionaries for Python. So structs are kind of like dictionaries. So we're going to store a person's first name as a string, his last name as a string, his age as an integer. But what if we want some kind of function to be able to operate on the information of that struct? We would have to have that living separately from the struct and then pass the struct to it. An object-oriented language that brings this class thing into existence would allow us to have all the stuff that would usually go in a struct stored in a class. But then we can also throw this new kind of animal in here called a function. So that new container that we have can hold all the stuff that a struct used to hold, but then can hold a little bit more. So then we might say, oh, well, why do we need structs then? Isn't a class kind of like a superstruct? So the Java people would say, look, if you want the equivalent to a struct in Java, no problem. Let me just steal this. Just create a class but don't put any functions in there. Isn't this class and this struct the same thing? They're holding 3 pieces of information. So the Java people would say, look, you don't need a struct. You got one. Just create a class and don't put functions in it. If you don't need functions, don't put them in there. And that's almost right. So the Java folks would have made the argument, well, let's put it on its, makes the argument that a struct is the same thing as a class without functions. So now, depending on who's right here, we get to decide who was the stupid one. Was C++ stupid for keeping structs? They introduced classes in C++. So if I could, in C++, you could use a class and put the same stuff in it that you had for structs and just not put any functions in there, and you have a struct. Java finally decided, look, we noticed something that the C++ people didn't notice, so we're going to get rid of structs. You don't need them. The reality is Java people are wrong. And it probably wouldn't make that big of a difference that often. But what is kind of funny about this is that in Java, one of its goals, we might say, is to make the life of the programmer easier. They do a lot more of the decision making for us. We don't, I mentioned that with C++, we are empowered to make bad mistakes. Java takes a lot of that decision making away from us. So does C#. They take a lot of the decision making away from us and just says, look, here's the only way to do it, and you're doing it the right way. Why? Because it's your only option. If you're going to do it, you're doing it the right way. In fact, as a Java programmer, you might not even know that it was the right way. You might not even know the way it did it, but just trust it was the right way. But this might come to bite you every now and then. We have this idea, and I've already referenced this once, called variable passing. How do we give information to a function? All right, and we've used the example of the invite to the party. Because keep in mind, we're talking about this stuff right now at a high level. You're going to see examples of this in Python. All right, so if you're at least loosely connecting these dots, that's good enough for right now. All right, because again, we're squeezing a lot of information into 8 weeks. Just is what it is. So we use this example. If you're inviting me to this party, you would hand me the address to where the house is, as opposed to the house itself. So if you're calling the invite function, you're inviting me to the party, you're going to pass that guy a value. Now, the smart thing to do would you be hand me the address to that house. So we have something called pass by reference or pass by address. Same thing. Reference is maybe the older way of calling it. Pass by address would be the more modern thing, but that's you handing me the address where your house is. Little tiny bit of information, right? That I can hold. That's not too heavy. And then I get in my car and I go and drive to the address. We also have something called pass by value. Okay? In a language like C++ as well as C, the programmer was responsible for explicitly choosing how they wanted to pass information to a function. They had to make that decision when they called the function. In Java, that decision is made for you. All right, so if we kind of add that in here, C/C++, programmer decides. Java, language decides. And the idea here would be that the language will always make the right decision. What does right mean? Probably the decision that's the most memory efficient. Okay? But now having said that, we have a little sticking point here. When we talk about structs versus classes, structs are passed by value by default. Classes are passed by address. All right, now what does that mean? If, let's say that I handed one of you the address to my house, and you're one of the folks that failed this quiz, so you're upset at me, and you decide at one of our breaks to run to my house and spray paint my garage. Am I going to notice when I get home? Yeah, you went to the real house. I gave you the address, so if you would take that information and go make changes to that place in memory, when I get home, I'm going to notice those changes. But if I handed you a copy of the house, I give you the value, the house itself. Like, look, my house is still safe and sound here. Here's your dollhouse. Hey, it looks just like my house. And you make changes to that, is it going to affect my house back home? No. If I give you the number 5, so I give you an integer, and I pass you the number 5, and you change that 5 to a 7. Does that mean the number 5 in real life has now become a 7 for everybody else? No, because I gave you a copy of the number 5. I passed it by value. Here's 5. Do with it what you want. This won't impact anybody else. But when you pass by address, that means you're working off the same piece of memory as everybody else's. So changes you make will be permanent. So understand here that if the default way that structs are passed is by value, and the default way that classes are passed is by address, that means that if you pass a struct to a function and you change the person's first name to Larry, that will not have a global impact. Typically, we would say this will not have side effect. It's usually the way they reference it. Okay, so if I hand you a struct and you start messing around with the values of that struct by default was handed to you by value. Therefore, your changes will not impact the original. But classes, by default, are passed by address. So if I hand you a class that I intended to use like a struct, I didn't put any functions in it, still has first name, last name, age, that kind of stuff, and you start messing with it, you're messing with the real copy. Because unless I was smart and I passed you a copy of it, I made a duplicate and passed you a copy, you're changing the real deal. You're spray painting my garage. That make sense? So this might not matter. If you're passing structs and classes to another function and you're not modifying the struct or the class, it won't make a difference. But if you do modify it and you expect them to act identically, they don't. That makes sense? So Java's position that a class without functions is pretty much a struct, I guess that's true. It is pretty much a struct, but it's not identical to a struct. They do behave differently when you pass them to a function. That make sense? Go ahead.
So the reason why I'm confused is because I've never really used structs before, but so what I'm trying to understand is, for example, if you have a struct called user and you have a class called user, if I go directly into the code and then I say, okay, I want to make changes to the variable of the struct user, that means that I'm only just making changes to a model and actually not the real thing?
Well, when you define the struct or you define the class, that's like a blueprint.
Right.
But now we're going to create one of those structs and we're going to create one of those classes. So now I have a struct that holds Mike Littman and I have a class that holds Mike Littman. All right? So this guy's name is S, this guy's name is C, struct and class. Okay? If you're a function and I pass you S, the struct, and you change my first name to Larry, you didn't affect the real struct.
So I didn't actually affect S. I'm only affecting
a copy of S. Okay?
Of S.
But if instead I passed you the class C and you changed the name to Larry, you did affect C.
Oh.
C is globally changed. Because this guy, when I handed it to you, unless I did something special, he came to you as an address by default. So you're changing the actual thing as opposed to a copy of it. They just behave slightly differently. And it won't make any difference if you're not changing them. Okay? But the punchline here for us, this isn't like some sort of deep knowledge that I expect you to fully understand right now. But I want to just kind of point out that Java really kind of made a misstep. To say that structs and classes are identical is not really completely accurate. They do behave a little differently, and as we're already seeing, and you're going to see once we get into programming, because when you get done with this class, you're going to know a little bit about a little bit. And even if you take the next class, the 537 class, you're going to know a little bit more about a little bit, right? So you'll know enough to be dangerous, but at that point, I mean, you've taken 16 weeks of programming. You have enough to maybe say, okay, I'm going to go and keep practicing this, and through years of experience, get better. Kind of the very first day of class, I referenced this to some like sports. If you're a soccer player, or you're a fan of soccer, or you're a fan of cricket, whatever it is, if you go to a 16-week cricket boot camp, doesn't matter if it's the best player in the world, you're not going to be a professional cricket player. Okay? You might know a lot about a little, or a little about a lot, but that still doesn't mean you can just sit there and go onto is it the pitch or the field? What's the cricket? What do they play on? They play on a pitch, the cricket pitch? All right, they play on the cricket. You're not going to be able to walk out there and play professional cricket. It's not in your wheelhouse yet. Maybe in 10 years. You got some really good lessons and you practiced for 10 years and you had some natural ability, maybe, right? Programming is similar. And keep in mind that I also know that. So all these things that I give you, these quizzes, the homework assignments, you're supposed to hate them. You're supposed to suck at them, right? Work hard, keep doing it. Don't cheat on stuff. You'll get through the class. It's going to be fine. I only seem mean on the surface, right? Well, I'm a little bit mean, okay? But I'm not just going to artificially fail you because you suck at something that you're supposed to suck at. You understand? You're not supposed to be good. You're supposed to be a little bit better than when you walked in. is the punchline. So given that we can kind of all accept right now that there's a lot of crap to programming, a lot of little nuances, right? The same thing's true, connected to your sports. If you're a casual, if I'm watching cricket on TV, I barely even understand how score is kept. But even if I understood the sport from a casual observer's perspective, there's little nuances there. Like somebody who's been playing it for a long time, they kind of understand the strategies that the batsman might use for this next, where they want to put the ball, right? These are all things that go into it that I'm not going to understand as a casual observer. Even if I think about American baseball, which I grew up playing, I only played it as a kid. So, when you have fans now, they're all into like the pitch count, how many pitches has this pitcher thrown, and the next pitch should be a curveball because of X, Y, and Z. There's a lot of extra stuff in there that the casual observer is not going to understand. Programming is the same thing. None of us are ever going to know everything, right? But we can at least accept that there's a lot of crap in here that you're not going to be able to memorize, so the only way you're going to get any good at it is just through practice. And it's things like this that I think can be kind of dangerous because it's now throwing you a curveball. If you expect these two things to behave the same, because Java's told you they'll behave the same, and then all of a sudden you run into a situation where you happen to be changing those values and they don't behave the same, you're confused. And you might spend a lot of time banging your head on the wall trying to figure out, well, why aren't these guys acting the same? Why isn't a class acting like a struct used to act? Java said I don't need structs anymore. I can do everything with classes. See what I'm getting at? So, call it a bug. Let's call it a quirk. However you want to think about it. These languages aren't perfect. All right, so, go ahead.
So how do you solve the problem of
In Java, what you would do is every object has a function called clone. So you can tell a object to clone itself, which will actually make a duplicate of it with a new memory address. And then you would pass that clone to the function. It's still being passed by address, but you're not breaking the original. So in that particular case, I'm like building a second house right next to my house. And I'm giving you the address to that guy. So when you, at the break, when you decide you're mad about the quiz and you go and spray paint the garage on that one, I'll come home and say, oh, well, he missed mine because he went to the clone. Makes sense? So it's still being passed by address, but the end result will be that the original was not modified. Something like that. So it's a little bit more wasteful from a memory perspective. Actually, you know what? It wouldn't be. Because when you're passing something by value, new memory is going to be created for it anyways. So that would be the fix. Just clone it and then pass it in. But, you know, this is one of those little bugs that if you introduce something like this into your program, you might bang your head on the wall for a while, not understanding why something is working one way, especially if you were an advanced programmer coming into this. Because then you may have written this with confidence thinking that, oh, it's going to act this way. And then when it doesn't, you're confused. When you're a beginner, when something doesn't work, that's just par for the course, right? Oh, I must have screwed up. Okay, but if you think you know what you're doing, then those are even more difficult problems to deal with. So it is what it is. It's something that doesn't really come up very often in everyday programming. It's one of those, 1% of the time you might bump into this. So most of the time it's not going to be a problem regardless. But when it is, it sucks because then you didn't remember it or, because this lecture is going to be in one ear and out the other. And I've run into this problem several times in the last 30 years, just by sheer volume of programming. And almost every single time it's happened when I was younger, I got stuck on it because I hadn't learned the lesson enough times until that's like the first thing. Now when I do it, I know how they work because I screwed it up enough times. We learn from our mistakes. And so when I'm writing this code and it kind of works the first time, it's not because I'm, just was born writing perfect code. It's because I've already made a lot of the mistakes. So now it's your turn to make the mistakes.
I'm curious, in Java, can you create structs?
Say this again?
In Java, can you create structs still?
No, Java does not support structs. It's off this list. C# supports that. So if we kind of go ahead and throw that in, because I mentioned C# versus Java, so let me go ahead and grab the Java slide here. And I'm going to rename this C#. So C#, object-oriented, has variables, has arrays, brought back structs. Brought back structs. Hold on, I'm in the wrong, sorry. Okay, so this guy brought back structs into C#. Now, there's something else that I'm going to show you here, just so we can kind of finish this conversation. I'm going to show you some C programming. I'm not going to quiz you over C programming. The stuff I'm about to show you, you're not going to be responsible for knowing, but it's for me to be able to close this loop. All right, it's an important kind of historical piece of this. So I'm going to open up my terminal here. I need to show it to you in C so I can tell you what Java took out. Okay, so I'm going to go ahead and I'm going to open up a file. So I'll do vi test.c. Oh, good. This is the last time I taught this, so good. So this is standard input output. I'm including in here. Don't worry about any of this crap. So I'm defining a variable named A of type integer. I'm setting it equal to 5. Then I'm creating here something called an integer pointer called B. Now let me reference what a pointer is here. Okay, so in most programming languages, like in your reading assignment, you read about types in Python, right? So in Python, we have integer types and floating point types and string types and list types and dictionary types, right? We have different types that are built into it. Well, in C and C++, we have a type called a pointer. Now, pointers typically scare beginning programmers. We already actually kind of referenced this because we said that C and C++ give you direct access to memory. And we decided that direct access to memory can be dangerous, and it's usually intimidating to beginning programmers. So there's even a better reason not to use C and C++ as the first programming language. Now what a pointer is it's a variable that knows how to hold a memory address. Okay, so it's no different from the programming world version of this. It's no different than me writing my home address on a Post-it note and handing it to you. But it seems a lot scarier when we deal with memory and computers. And what's even funnier than that is our address system in real life is far more complex than the address system in computers. In real life, we have like a street number, right? And then you have a number, then you have a street, and you have a town, and a zip code, right? You have a bunch of pieces of information that all add up to where you can find that person's house on Earth, right? That's pretty complex. With computers, everybody lives on one big long street. And if you're house number 17, well, we just walk down the street till we get to house 17. That's where you live. There's no zip codes. There's no street names. No city names. Big long street. Make sense? So actually, memory in computers is more easily organized than real life memory addresses, real life addresses for houses. But because we're comfortable with real life, computers feel intimidating because we have all crazy hexadecimal values and stuff like that. So pointers give us a variable for holding memory, holding a location in memory. All right, so that's what a pointer is. Going back over to the C thing here. So here I'm defining a variable. I'm defining a variable named A. So that's the name of my bucket. It's capable of holding that kind of thing, an integer. And I'm going to put in there the number 5. Here, I'm creating another bucket called B. This guy's capable of holding an integer pointer. This is a special syntax specifically for dealing with pointers in C and C++. And what am I going to put in there? I'm going to put the address of A. So again, this is another special syntax. Ampersand A says, give me the address where this guy lives. And store it in B, which is capable of holding a memory address. Make sense? All right, so then when I come down here and I print out, so this is saying A is, %D is going to be the value of A. So that should give me a 5. Star B is the value at B, which is also going to be a 5. And let me show you that here. Actually, let me, well, I'll show you that real quick and then we'll, oh. So A is a 5, star B is also a 5. Star B says, give me the value at address stored in B. The value at that address was a 5 because B holds the address of A. Make sense? Now if I go back in, third time's a charm. If I go back in here, and I change
Percentage D.
a decimal. It's a placeholder for a decimal. So if I go in here and I say the address of A, I'm going to go ahead and say %P for pointer. And I'm going to print out the address of A. And then I'm going to say B, %P for pointer. And I'll show whatever's in the variable B. B holds an address because it's an integer pointer. So B is going to be an address. Address of A should be the same address. Address of A is the place where A lives in memory, not the value at that place. All right, so same memory address, and these guys to a person look scary. When it's just the big long number, just happens to be in hexadecimal, and that makes us nervous, right? But actually, that's just a big long number. It's the house way down the street. One street, it's just way, way down there. Get in the golf cart. You zip down the street. All right, does that make sense? We're not learning C in here, but what I wanted you to understand from this is in a language like C, we have a syntax for working with pointers. Specifically, we can directly manipulate memory using the asterisks and the ampersand. Those two things allow us to move in and out of memory. Okay? Now, when I teach Java courses, I typically will not use a textbook unless I've vetted the textbook beforehand. And the reason I say that is many Java textbooks claim that pointers don't exist in Java. That's not true. In fact, most things, well, here, let me just show you that real quick. We're playing this game. Let's do vi test.java. Just write a simple little Java program here real quick. Here, let me just explain what I did here. So I went ahead and I created a list in Java using Python lingo. This is an array. And then I'm just printing out whatever stored in AR. Okay? So, and if you want to, here, I'll do something else here too real quick. I'll go ahead and I'll say AR at bucket 0 is equal to a 5. AR at bucket 1 is equal to a 6, something like that. So when I print out AR, a beginning programmer might say, oh, you'll see a 5 and a 6 printed out, right? Because that's what I put in there, seemingly. Memory address. Right? That looks like a memory address-y type thing. Does that look like memory addresses don't exist in Java? I didn't have to write a very long program to show you a memory address, did I? Okay, so when a book says pointers don't exist in Java, well, we just saw one. Saw it in the wild. What they really mean is Java lacks a specific syntax for working with pointers. Java's taken away that asterisk and that ampersand from us so that we can't directly work with memory. Java makes the decision. If you have a variable and it holds memory, it's memory, whether you like it or not. If you have a variable and it holds a value, it's a value, whether you like it or not.
So what if I have an int that is not declared? Does it do the same thing, or does it just print out the null?
What do you mean an int that's not declared?
Like an integer x or something. If I have x.
Do you want me to give it a value?
No value.
Okay, well, it's going to get a default value of 0 probably. In fact, it'll probably complain that it might be, but so I'll just throw a 7 in there for whatever. So this is a good example. If I say print out X,
It's going to print out.
it'll print out a 7.
But I was wondering if you just did it with that.
If you didn't do that, we're probably going to get a warning that says variable may not have been initialized. But if we don't, it's going to be given a default value of 0 typically.
What if it's
Yeah.
declared string?
Might not have been initialized. Well, string is going to be the same thing.
So,
You know, any variable, if I say string S and don't put a value in it, it's going to give me that same warning saying, hey, you're trying to use something that you never put something in. It's going to give me that warning. But the punchline here is if I come here and I say equals 7, and then I go to print out X, it will be 7 because Java treats integers by value. Java treats arrays as addresses. Make sense? When we talk about lists later on today, you'll understand why they're treated as addresses. Okay, but for right now, what's important for us is it's not that pointers don't exist in Java. What doesn't exist is a specific syntax for working with them. That makes sense? That's what we're missing. And that's okay, because most of the time, Java makes the good decision for us. Java doesn't let you pass somebody the house. If you want to pass an object to somebody, it's the address. Because we've said in real life, 100% of the time, it would make sense to pass somebody the address where your house is, not the house itself. What Java then has done, though, is they've taken away that ability for the programmer to say, look, I know it doesn't make sense, but because of the problem I'm solving right here, I actually need to pass the house. Java won't let you do it. Right? Now, we're saying it pretty much never makes sense in real life, but now we're dealing with computers. And maybe there's some strange situation where you have to do something and look, I don't want the address. I need a copy of it. And that's when, like he was asking earlier, that's when maybe you create a clone of it. So it acts like a copy from a I'm going to change it locally perspective. So you have to go and do a workaround for it. Where in C and C++, you have those extra couple little tools where you could say, have at it. Here's a copy of it. Go to town and do something with it. Does that make sense? You just don't have that option in Java. So you have to roll with that punch. It's just the nature of the tool. All right. All right, so let's I just want to go a little longer here. How many of you are Android users in here? 2.25 people. How many are iPhone users in here? Everybody else? Okay, that's actually a little more lopsided than it usually is. Typically, you get like half and half, right? More than likely, if you're an Android user, you say Android's the best, and you either hate or strongly dislike Apple. If you're an iPhone user, you think Androids are stupid, or somebody gave it to you as a gift or something like that. So it's not constructive to say which is better, right? In fact, today it's really not constructive because they're both very good. In the early days, iOS was better. And there's a good reason for it. We're going to talk about that. I'm going to kind of go through this a little bit quick so we can get to the... So which came first? iOS or Android?
Android.
All right, fight to the death. iOS came first. Yeah, Android was about a year later. And it actually was a lot of the reason why Android was not very good at the beginning, contrary to what the Android people would have told you. I write software for both of them. Right now I'm carrying an Android phone. I carried an iPhone for years. My wife still uses an iPhone. So I'm as impartial as you're going to get. Okay, I've written software for both of them since they came out. All right. Android sucked for a while is what it comes down to, regardless of what, whose lemonade you were drinking. All right, so here's the deal. So iOS came out first. Android came out about a year later. So now, this was a while ago now, right? This is 11 years ago. So we're talking about this stuff, and Android's been out for a little bit less than a decade. It wasn't quite a year. It was like a year and a half, but whatever. In the early days, you would see commercials, Android versus iOS. You don't see them so much anymore. You notice that? If you watch if you watch TV, you don't really see those, iOS hates Android commercials and Android hates iOS commercials. They've kind of gone away. And that kind of supports what I said a few minutes ago. They're both really good now because they've learned from each other for a while. And Android's caught up and fixed some of their problems. And Apple's even started taking some stuff from Android. All right. But if we go back to the early days, you had a lot of, so we had what? We had 3 people in here who are Android users. Why are you an Android user? You said you were Android, right?
Yeah.
Why are you an Android user?
I just started with it. I just stuck with it.
Okay. All right. You're an Android user too?
Yeah.
Why?
I think I started using it and everybody's Apple before, so I was like
Okay. How long have you guys been using Android? How many years?
5, 6 years now.
6 years. Okay. We had another Android user over here. All right. So why Android?
Easy to use actually.
Easy to use. Okay.
It also gives you more access.
How long have you been using Android?
I think since the beginning, like 8, 9 years.
He's my target. All right, good. You guys can be mini targets. All right. Prepare to be tricked, by the way. All right. But this is good because this gives us some background information. All right. So when Android first came out, so we talk about Android, I'll just put 2 different categories here and then so when Android first came out, the thing that they said was bad about iPhone was Android supported Flash and Android supported multitasking. What does it mean to support multitasking? You have more than one program running at once. How many of you listen to music on your smartphone? Pandora, something like that? Now, what if, in order to listen to Pandora, you had to have the Pandora app actually open? You couldn't do anything else on your phone. Would you like that? That's how the iPhone was for a while. Didn't support multitasking. If you wanted to listen to music on Pandora, Pandora had to be open. Now that's not the case. We'll talk about that in a few minutes. But from day one, Android supported multitasking. You could have as many applications open as you wanted. Okay. What does it mean for Android to support Flash? What is Flash?
No, but it's a play.
Who?
SD card.
No, not a flash card. It's software. But that's not inaccurate, just not the flash I'm talking about. So I'm not talking about SD cards, and I'm not talking about the dude from the TV show. Okay? I'm talking about a piece of software from Adobe called Flash. It's multimedia stuff, right? So if you go to like Yahoo Games or something like that, so when you go to a website, sometimes they have Flash-based stuff on there where you can drag stuff around and things like that. So in the early days of smartphones, Android supported Flash, iPhone did not, and that was something they bragged about in their commercials. All right. So do you like the fact that Android supports Flash? Like, do you use it? Is that even today?
Yeah, like good to have that.
Okay, so I'm going to get back to that in a few minutes. All right, so these were the things that were good about Android, that they would have said iOS is bad because it doesn't do these things. iOS did not support Flash. iOS did not have multitasking early on. And iOS took heat for the multitasking thing for a while. People were like, Android's had it since day one. Why is it taking Apple so long to have multitasking? It makes sense in a second. What do you think the iPhone people were saying about Android day one? What was bad about Android? Maybe a little less polished. Forget about that. That's personal taste, maybe. We'll talk about kind of why, but battery life. Android's battery life at the beginning was terrible. And it's very, very, very related to that. And here's why. I mentioned a few minutes ago that Android was kind of rushed to get done because Apple had already come out and they were doing quite well. And nobody knew that iPhone was going to be as popular as it was. Apple doesn't make phones, they make computers. But obviously, that's in the history books now. So Android is based on an operating system called Linux. So what they did is they took an operating system called Linux and they tried to make an interface for it that was made sense on a smaller device, a phone. Now, is Linux a good operating system? Yeah. Linux is great. Servers use it all over the world and stuff like that. So don't you think Linux's multitasking model would be good? Sure. It's great. So what's the problem? Does Linux's multitasking model assume that your computer's plugged into the wall? Yeah. It assumes you have constant power. So do you think when Linux was making their multitasking model, do you think they paid a whole lot of attention to what's going to preserve battery life? They didn't pay any attention to it. So the multitasking model for Linux was never designed to be run off a battery. It assumed your computer was plugged into the wall. So now you're running that thing off a battery, and it just drains like nothing. Now, by the way, this bad battery life thing also related to Flash. I'll talk about that here real quick as well. And this even happens today. First of all, Flash is not very popular today, right? It's been kind of replaced by HTML5. In fact, most web browsers now do not ship with Flash anymore. If you happen to go to a page that has Flash, you have to go download the plugin. But an interesting experiment, you can do this yourself. Download Flash on your laptop. So, my laptop is supposed to get, let's call it 8 hours of battery life under normal use. I mean, I'm playing a video game or something to go less, but if I'm just using it, get 8 hours of battery life, let's say. Let's say I go to a page that just has a simple little Flash thing going on it. What do you think my battery life would go down to? Half? Not that bad?
I assume it wouldn't be that bad, especially if you're
Probably would go down to less than an hour. It would destroy the battery. Flash uses a lot of system resources. And it's not because Flash is inherently bad. Flash was doing some pretty magical stuff pretty early on. It was way ahead of its time, but now it's very old. Make sense? There are better solutions now than Flash. HTML5 is one of them. Apple stuck to their guns and said, look, we're not going to support Flash. They supported HTML5 since day one when HTML5 was not popular yet. Now HTML5 is popular. So everybody uses HTML5 now, and that's kind of where we come back here. Android around year 3 or 4, I think. So I guess probably 6 years ago, somewhere in that ballpark, stopped bragging that they had Flash. Now, Apple has never had Flash. But Android stopped bragging that they had Flash because they took Flash support out. Android has not supported Flash in over 5 years. Google never mentioned that, but go to a site that has Flash on it, it won't work. The mobile version of Flash is even worse than the desktop version of Flash. Destroys batteries. And it wasn't even that usable. I mean, if you had to, if you were on a site that had Flash, that had something Flash on it, and it was mission critical that you needed to be able to use this site, sort of, you probably could have gotten by with Flash on Android. But not much beyond that. It wasn't a good user experience for Flash. Now, Again, Android supported multitasking, but iOS would say that Android's biggest problem was battery life. Now, Android came out with its App Store year 2. Shortly after Apple came out with theirs. So Apple came out with their App Store about 6 months later, 8 months later, something like that. Android came out with theirs. So neither of them had App Stores the first year. They were both just whatever came with the app. So you had things like Pandora, the built-in applications. Now, what was when the App Store went live for Android? What kind of app do you think was the most popular app on the Android App Store? There was a whole bunch of different versions of this app. They all kind of did this exact same thing. Pretty related. It was apps to close other apps. The most popular apps on Android for a long time were apps that allow you to quickly kill other apps that are running on your phone. Because using Android, it's not all that convenient to go in and close running apps, to truly close them. You can kind of hide them, but they're still running. They're still taking battery life. So the popular apps were apps to close other apps, so that you had a battery life that was even reasonable. And this wasn't because Android was bad. It was because Android was based on a desktop operating system, whose multitasking model was written for desktop operating systems, not mobile operating systems. So now it starts making sense why Apple didn't support multitasking early on. And even today, you can make an argument that it doesn't really support multitasking. The way Apple did multitasking was a mobile-first way of doing multitasking. So they decided, what should multitasking look like on a mobile device? Because generally speaking, you're not running 2 applications at once, side by side. That's become more of a reality now, right? iPads can do that, and some of the larger Android devices, Android phones can do that. Like I can run 2 applications next to each other on the Note 8. But that wasn't until very recently. So you were never in Android actually running 2 applications at once. You just were running one application, and then behind the scenes you were running another 30, just burning battery life. So what Apple decided when they finally came out with multitasking is they said, you know what? They identified like 8 things that an app might want to do in the background while it's running. The most obvious one for us, and the one I'll just mention, is it might want to play music. So when you put Pandora into the background, for example, that app could choose to register with the operating system. And one of the hooks they could choose to register with was play music. So a very small portion of Pandora could remain alive in the background playing through your playlist or whatever on Pandora. That makes sense? So the entire application was not running in the background. It was really leveraging the operating system that was running already to play this extra stuff. So much friendlier to battery life. Now, today, batteries have gotten lots and lots better. So one thing you might notice is when new phones come out today, what keeps happening? The screens keep getting better. The screens keep getting bigger. The phones pretty much stay the same size. And the battery life stays the same. So they squeeze more battery into the same size container, and they need the more battery to support the new stuff, the better screen, brighter screen, blah, blah, blah. And then they just say it has the same battery life. We haven't gotten better battery life on phones in a while. We just keep getting the same battery life with more stuff because the battery inside it is bigger because we've gotten better at squeezing batteries into stuff. You know, that's the whole thing with Apple's MacBooks. You know, most of you who don't have a Mac out there have a removable battery, right? You know, you can take your computer, and if your battery starts wearing out, you pop it out, you go to Best Buy or whatever, or get a new battery, you pop it in, and you got a new battery. Well, typically the battery life on your laptop probably isn't advertised as being as high as the battery life on a Mac might be. This doesn't have a removable battery. Why not? Well, you might say, well, Apple, you know, they're all into aesthetics and stuff, and they want things to look slim and all that stuff, so that's just an eyesore to have a removable battery. But when you have a removable battery, like on the bottom of your laptop, you push a button or something, right? And the battery pops out. All that stuff, all those mechanics in there that have to hold the battery in, takes up space. Apple said, we could use that space for more battery. If you were to pry this thing open, most of what's in here is battery. You can't replace the RAM in this. You can't replace the hard drive. All of it is soldered on the board. A majority of this is battery that's in here. Like no moving parts. So that's how they get the longer battery life. They say, look, the user can't upgrade anything because it's all just soldered together with just sitting next to a gigantic battery. And the user can't do anything. I can't put more RAM in this. I can't change the hard drive. I can't change the processor. I can't change the video card. I can't change the battery. I can't change anything. But I get good battery life. As long as I'm not running Flash. Or like a video game or something like that. All right. So those are the things that Apple would complain about Android, is that they didn't have good battery life. Now, you mentioned that maybe Android, and this is still probably true today, but to a significantly lesser extent, that Android maybe doesn't look quite as good as iPhone. And maybe where that's best seen is if you open up the same app on iOS and the same app on Android. Let's take like the USA Today app or something like that. The app on iPhone looks a lot more polished than the same app on Android. Now, the people who wrote the USA Today app are probably pretty competent, right? And there's lots of people who use Android. In fact, most people say, oh, it's like 50-50. Actually, Android has more than 50% of the market for Android install base. But Apple, if you're talking about the newest version of the operating system, Apple blows away Android. Android is very what's called fragmented. That's what I'm going to put on here. Android.
Application, if a company is putting out a new application, usually always comes out on the iPhone first. Or if there's
well, and there's a good reason for that. Like, so my software company, when we write apps, I mean, we're usually writing it for both iPhone and Android. We almost always write it for iPhone first. So we get all the graphics right for iPhone, and then we go and figure it out on Android. Now, Apple used to complain that, Android's very fragmented. They don't mention that anymore because Apple's become a little fragmented, and we'll talk about what that means here in a second. But first of all, Android is an open source operating system. But Google doesn't make phones, so until recently. Now they make the Pixel, but they actually use another company to make the Pixel. But regardless, a majority of Android devices out there are not made by Google. Right? So generally we would say that, and Google makes Android. We would say Google is solving the old Microsoft problem. Google solving the old...
Here's what I found on the web.
Thank you. They're solving the old Microsoft problem. That is, they're writing an operating system that has to run on a whole bunch of other people's computers. Right? So Google's wrote an operating system that has to run on my Samsung computer. Okay, Google's writing an operating system that has to run on somebody's LG computer. Replace brand of your phone with whatever. So now, my phone has a gigantic screen on it. Your phone might have a smaller screen. Something like that. Your phone might have some physical buttons. Some phones don't have physical buttons. So every phone has different kind of equipment in it. Some are faster, some are slower, some have, radio bands for X, Y, and Z. Some have something else. So we don't know. Some have front-facing cameras, some don't. All sorts of different things. So Google is writing this one operating system to run on all sorts of pieces of hardware. That's a hard job. So when you consider that, Android's actually pretty good. So even if we look at Android versus iOS today, even if we say, look, we're going to give the nod to iPhone for maybe just being a little bit more polished. Things are just a little bit better across the interface. And apps typically look better on the iPhone. Now, if we went back to the earlier days of Android, it was a lot better. Today, it's pretty close to a coin flip. It's not like things look like crap on Android, right? They're fine. Especially when we consider that Android had to make that app look good on 500 different devices. Android had to make it look good on 3. Or iPhone had to make it look good on 3 devices. All right, so Google is solving the old Microsoft problem. When we say Android is fragmented, we're talking about different size screens. Actually, let's just start with different here, and that way I can just kick it in. So we have different size screens, different pixel densities, different screen resolutions, different onboard hardware, so on and so forth. Different. And we're expected to have these apps look decent on all those different screen sizes, all those different speed devices, blah, 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 blah. For a long time. So the iPhone, the first iPhone, the iPhone 3G, the iPhone 4, those devices were all had the identical size screen. Screen got better with the iPhone 4. Doubled pixel density, so it had the Retina display, but the screen size was the same. Just kind of double the resolution, but doubling the resolution is fine because it's the same aspect ratio. So people would just design their apps to work on the 4, and then they would just have it to look right on the older ones. No problem. Now, then the iPhone 5 came out. The 5 was almost the same screen size. They just made it a little taller. So it was the same width, made it a little taller, and apps by default just had these little tiny bars on the bottom and the top. So if you chose not to do anything to your app, you just decided, look, I'm going to rate my app so it runs on the through the iPhone 4. It'll run on the 5 and the 5S, no problem. Right? It's pretty much the same screen size. If you wanted to use that little more screen real estate, that's fine. It wasn't a deal breaker. You still had mostly the same resolution. Then the iPhone 6 came out. The iPhone 6 is when the iPhones started looking more like the physical size of the Android devices. For a long time, iPhones were, in general, smaller than all the new phones coming out from Android. Now, you might say, okay, well, they were nicely built and all this other stuff, but pretty much 4.7-inch diagonal became the standard for Android devices. Most new devices were that. You might have some different resolutions and stuff, but they were pretty much that. So iPhone 6, 6S, 7, 7S, 8, 8S, all have the 4.7-inch aspect ratio, or 4.7-inch diagonal screen. So 3 different size screens on iPhones, really 2.5, something like that. Then you have the iPads. Now, whether you're dealing with a normal iPad or an iPad mini, it's the same screen resolution. So not that big a deal. They have a different interface anyway, so you really only have one device you're designing for them. Things got a little loopy now that we have the iPad Pros that have a lot higher resolution, so things get a little wonky, but we're still in the same neighborhood. So Apple is more fragmented now than it was, but it's not as fragmented as Android in the big scheme of things. But generally speaking, if you look at Android devices today, most of the devices now are kind of the same size. For a long time, Android devices came in all sorts of shapes and sizes. You had little mini ones, but now basically you go out and get a smartphone, you get a normal one, which is 4.7 inches, or you get gigantic one, which is like 5.5 or 5.7, something like that. You kind of have 2 size-ish, right? So Android's kind of become less fragmented. Apple's become more fragmented, and if we had to choose who's more fragmented today, it would be Android is more fragmented just because you have the sheer number of people making the hardware. But they're both reasonably fragmented today. So writing apps for them today isn't as big of a deal. But that's kind of where the app, and then the app creation tools. So Android Studio, especially their interface builder for making Android applications, which we do work with in the next class. So if you're interested in Android applications, we do that in 537. We write Android stuff in there. But in any case, that tool is just not as polished as Xcode, which is what you use to create iPhone apps. And it's not even the programming aspect of it; it's the interface builder where you drag and drop buttons on and stuff like that. Android Studio is way better today than it was a year or two ago, but it's still nowhere near where Xcode is just for building interfaces. And that's okay, but that becomes kind of one of the weaknesses. Just the development tool is not as refined.
What version of Android does Android Studio run on? Is it like Android 5 or something? Android 4?
Well, what do you mean? Like you can target any version of Android with it.
Okay.
Current version of Android Studio is like 3.0.1 or something, but you can choose which version of Android you're writing your software for. Because the idea is when you write an application for Android, you're targeting an Android version. So, for instance, if you decide, I'm going to take advantage of something that's in the latest, greatest version of Android, which is Oreo, Android 8.0. Anybody have a Pixel in here? A Pixel 2, rather. Okay. So none of us in here have the latest version of Android. None of us. I got a Note 8, which is Samsung's current flagship phone. I don't have the newest version of Android. It's not out for it yet. Because this phone runs the Samsung version of Android. They get Android and then they add Samsung bloatware to it. So I'm waiting for them to add their Samsung stuff to it. The only phone right now that runs Oreo, Android 8.0, is Pixel and Pixel 2, the Google phones that run it natively. In any case, when you write an Android app, when you first start it, you choose which API you're going to target. So if you target Android 8, which is the latest version, your app will only run on like 0.1% of all devices. Because only 0.1% of all devices have Android 8 on it. So typically you would target something like Lollipop or something like that, which is like Android 5 or 6 or something like that, which covers 98% of devices or something like that. So all devices that are currently working today have at least that on it. Okay, so that's kind of the Android iOS story. All right, so let's take a break. Let's take, I don't want to take too long. Let's take 7 minutes. So we gotta keep trucking through some stuff. So come back at 8 o'clock, and we'll get through the C# versus Java stuff.